Okay, so this session is called the design and analysis of machine learning, in which we look into how do we design the experiment, and then how do we compare the performance of the algorithm, how do we split the data, and so on. Some of the parameter used in our modeling tasks um, include cleaning the data and also dividing your data into training and testing data and getting the accuracy, and then how do you evaluate the performance of the um, algorithm. Okay, so now you should be able to perform a problem dealing with regression or classification or clustering. So this session will look into how do you evaluate them. Okay, so a question like assessment of the expected error of a learning algorithm, is the error rate of 1 and n less than 2%? So this is sample of question that could be asked by you. Okay, so you are looking at whether the error rate for the k and n, k equal to 1 is less than 2% or not, or you want to compare the expected error of two or more algorithms. So in this example, we want to know whether the k and n is more accurate compared to the multi-layer perceptron. Okay, so we are using the same data and we are performing the classification. So we are taking two algorithms and we will compare the performance based on the accuracy. Okay, so every time when we want to model our data or train our data, we look at the training data set. We also look at the test data set. And if you have a separate data, that is what we call the validation data set, which is coming from different uh, data set. So if you have a data set and then you divide them into two, so this is your training and this is your testing. Okay, so it depends on how many percent you want to divide them. For training, normally you go for 70% and 30%. Okay, but if you have a similar type of data, so you once you model them, once you model your data and you have trained your classifier, then you feed in the same domain data, but from which is different from here. So this is what we call the validation data set. Okay, so you want to know that whether you get the same accuracy or not if you use other data with the same domain. Okay. We also have this resampling method. So the major reason why we perform resampling method is that we want to have enough data for us to test your classifier, and also we want to have reliable result. So we will perform a k-fold cross validation. So k refer to how many number of fold or partition that you want to divide your data. So we will look into this. Okay, so when you want to perform any experiment, so if you look at some data, so when we say the application dependent, it refers to the domain of your data set. So we will look into what is the misclassification error. No. Sometimes they call it risk or loss function. So what we wanted to do is we want to reduce this loss function. How much improvement can we make on the accuracy by changing the parameter? So in most cases, when we have proposed a classifier, we will say, how do you optimize the result? How do you um, ensure that you get the optimal value for your classifier? Okay, so the aim is to reduce. So that's why when you have chosen your parameter setting, you need to justify whether the parameter setting that you use can give you the optimal value of accuracy for your classifier. We also look at how much time do you need to train, and then how big is your data. So space complexity are referring to, because we are looking for the solution. So the space referring to the data that we have, and then we are looking at all the combination of data that we have in order to get the best accuracy. Okay, and of course it also involves testing, because these two are required, because we have the train and testing data. Okay, and how do you interpret them? How do you interpret the result that you get? So we will look into the ROC, uh, receiver operator characteristic, in order to look at the performance of individual classifier. Okay, and fifth one is how easy for you to program them, how easy for you to reapply the algorithm for more testing. And then um, this one referring to the cost sensitive learning, refer to how much parameter that you need to change in order to get the best result. So you have to list out, you say all these are control parameter, and you also have uncontrolled parameter. So the control parameter, you will change the value and look at what is the best value for the control parameter. Control parameter meaning that parameter that you are able to change. Okay, uncontrolled parameter referring to parameter that you cannot change, already fixed. Okay, so when we have the input here, we have all the controllable factor. Okay, so these are the parameter that we can change or manipulate. We also have some which is uncontrollable factor, in which they are used just like that. Okay, so but the good thing about the uncontrollable factor is that they introduce randomness. For example, when we perform the sampling, the random sampling. So that one we cannot control, because they will pick randomly from your data set. So this random selection will introduce randomness. Okay, and this parameter setting, which is controllable factor, you can change. For example, for k and n, so you can control what is k. Or for the neural network, you can change the epoch, you can change the percentage of um, dropout. Okay, so you can also change the number of iteration, and so on. So the final output that we get here must be some output that maximize the response. Okay, so what we want to find is, we find the configuration of controllable factor, because we want to configure this and maximize the response, maximize the accuracy, and minimally affected by uncontrollable factor. So since this one we cannot control, so what we want to do is we want to minimize any effect caused by this uncontrollable factor. Okay, so we want to optimize this output based on this parameter. Okay, so when we talk about the search space, for example, if we start from here, we have many approach. The first one is the best guess. So best guess refer to some greedy algorithm that said that if I go here, I will get a better solution. Okay. We could also have what we call one factor at one time, meaning that if I'm here, I can go to the right or to the left or up and then go to down. But I can go straight here or up or left or down. Okay. Okay. The factorial design, meaning that we will explore all the possibility. So this is exhaustive method. We will try all the possibility. Okay. So of course, this one will be based on certain computation. This one is based on where you are at that particular time, and this one to ensure that you cover everything. So this is more expensive lah. Okay. So when we say the search space, it refers to the solution to your problem. Okay. For example, you want to get the optimal value for your classification for your neural network, but there are so many parameter setting that you need to change. So that is what we call when we go to this area, meaning that we are using certain parameter setting. If we go here, meaning that we are going to different parameter setting. So what we wanted to look is we want to look for the best uh, setting, the best setting for your classifier. Okay. So the guideline for machine learning experiment, you have to look at what is the aim of the study. Do you want to perform regression? Do you want to do classification? Or do you want to do clustering? Okay. And also you will look at what is the variable that you are looking at. So depending on your variable, it will determine what type of problem you are dealing with. Some other regression or classification or the clustering. Okay, and then you also have choice of factor and level. How many parameter that you want to look at? Okay, and also what are the range of the parameter that you will be dealing with. You also have to look at the choice of experimental design, like how many k-fold you want to perform, what is the percentage of training and testing, and so on. So that is what we call the design. Then you perform the experiment, and then you perform statistic analysis on the data, and then you conclude. So basically, all these things you must be able to respond to all of this section. Okay. So for example, like this, for the resampling, we normally come across with this k-fold cross validation. What does it mean? So k-fold meaning that how many partition you want to do for your data set. Okay, so in this case, we are looking at this is your training data set. This is your validation data set. Okay, so if I say that I have k-fold, let's suppose we have 5, okay, 5-fold. Okay, so meaning that I will have 5 validations. So this is up to 5. Okay, so what I have is that this one I will do as my testing. So I take the one part. So basically, I will have 5. So I will have 5. Okay, so the x1 here will be used as my validation, and the rest of this will be used as my training. Okay, and then I will take again this for my validation, and then the rest of this will be used for training. Okay, so if we summarize that, for each of the TI I have, I I will share the k minus 2 parts. So for example, like this, compared to this. So between this 1 and 2, I will share this. These are the same, right? So meaning that I will not include 1 and 2. So here we have x4 and 5. So basically, this is 3. So 5 minus 2 equal to 3. So that's what it meant here. So this is what we call k-fold cross-validation. So if someone asks you what is your k, you said 3. So explain why 3. Okay. So this also can be used in your design, saying that I will perform k equal to 2, k equal to 3, and so on. Okay. Sometimes you also have this 5 times 2 cross validation. So 5 times 5 meaning that you are repeating this 2 cross validation. Okay. So because when they select the data, they select randomly. So you will repeat them 5 times lah. So this is 1, 2, got 3 here, 4, and 5. Okay. So this is 5, 2, and 1. Okay, there is another called bootstrapping. This is normally used for the ensemble. Uh, ensemble in which we combine a few classifier. We have discussed about that one. So for bootstrapping, they select instance from a dataset with replacement, meaning that you select that row to be one of your training dataset, and then you put them back, then they could be selected again for the next one. So you could have a duplication in your training dataset. Okay, so based on this bootstrapping, it says that we only have 36.8% as a new instant that you get. This one related that you do not pick an instant after end draw. So you may have 60% of them repeatedly the same data. So we use bootstrap in the case where we don't have enough data set, or we introduce randomness lah. Okay. Okay. When we try to compare the performance of the classifier, we normally use um, the error rate, recall precision, and specificity, and also false alarm rate. So these are computed based on your metrics here, confusion metrics. So confusion metrics mention about, okay, you have a true class here, yes and no. You also have the predicted class here, yes and no. Okay, so here we are looking at a true positive in which the true class is yes, but it also predicted as yes. So this is what we call true positive. So the same thing goes to the true negative here, in which the true class is no, but also predicted as no class also. Okay, so when the true class is predicted as no, so that is what we call false negative. And then when we have a true class of no predicted as yes, so that is false positive. Okay, so the error rate will be number of errors. So number of errors will be false negative and false positive divided by the total number of data you have here. This is n. So this is the error rate. And then the recall is number of found positive and number of positive. So this is normally introduced in information retrieval. Okay. But for the classification, we are looking, we call it sensitivity, the hit rate, where we look at the true positive divided by the true positive plus false negative. So we are looking at here. The true positive divided by the sum of this. Okay, so here. So if this is 0, so that means you will have 1 because your true positive is 1 and true positive is uh, no they are same value, so you will get 1. Okay, okay. The precision looking at number found positive divided by number of found. So this is looking at only the positive. So the positive one will be here. So we are looking at the predicted class yes. So true positive divided by true positive plus false positive. So we are looking at this portion. Okay. So we want to minimize this. Okay. So if this is 0, so you will get precision equal to 1. So the precision will look at here. And then specificity will referring to here. So we want to minimize the false negative here. No, this one, yeah, this one will refer to here. True negative and false positive. So it will, let me erase this confusing. Okay, so specificity referring to this. So for the class no. Okay, so we want to reduce this false positive. So if this is 0, so we are looking at 1 here. So if this is higher, meaning that we are looking at the no class. Okay, and this one refer to true positive. It refer to here. So this one refer to here. Okay, and we also have the last one, which is false alarm rate. So the false alarm rate will look at the false positive, which is this one, divided by false positive and true negative. So which is also refer here. So it's the other way around lah, because terbalik juga. Okay. Okay. So this is another way how we compare the algorithm, but we can go next level, which we look at these values. Okay. So we for the ROC ataupun receiver operating characteristic curve, we are looking at the true positive rate and also the false positive rate. Okay, so let me move forward here. Okay, so this is the ROC curve. So this is the true positive. Okay, so up we go up here. So the true positive is going to 1. So meaning that you want to have all your true positive to become true positive lah. No, to get your true positive to be 1. So true positive, no. When you are here, your true positive is 1. So meaning that you manage to get all the true positive correctly classified. When you are here, so meaning that your true positive is 0. So we assume that all your sample are negative here. When we are here, saying that my true positive will be 1 and also my false positive will be 1. So half of your the data is true positive and the other half is false positive, meaning that all your data here will be positive. So the best one is here. We want to maximize this. Okay, so the bigger area you cover here, the better they are. So if you go back to this diagram here, so which one is better? A, C, B. So can you type which one? You type A, B, C lah. So which one will give you better um, performance? C or B or A? The rest? C. Okay. So definitely not A lah. Okay. So the answer is we want to measure area under the curve. So the one covered by B or C. Okay. So the best answer will be when with lower positive rate, you get B as a better algorithm. But for higher false positive rate, you get C as your best classifier. Okay? But you can measure area under the curve and tell you which one is better. But you may explain also for lower false positive rate, then B is better. But for high false positive rate, C is better. Okay? We also use precision and recall. So those who have studied information retrieval, so this is the one that you study. So for example, for precision, we are looking at relevant document retrieve divided by relevant document plus B. B is the retrieved document. Okay, so how much the retrieve document relevant with respect to your query. And then for the recall, it looking at what portion of your document that has been retrieved as relevant, because C referring to all the relevant record. So both can be used in order to measure how well is your system works. Okay, so now we look into the ROC. How are we going to use that one to evaluate the model? I will skip this one. This is similar to what you have seen before. So this is the confusion matrix. And based on the confusion matrix, we can measure the accuracy. So we are looking into this true positive and true negative, and divide by the total of all this. Okay. But the problem with this accuracy is that if you have imbalanced data in which you have one class has 9,990 and the other class only have 10. So when you perform the prediction, you get 99.9 if all of these are not classified correctly. So 10 lah. But you still get this one all correctly classified. So you still get 99.9% accuracy. So this is misleading because your model does not able to classify this one. Okay. Okay. Now we look at how do we use method for performance evaluation. So we will look into the class distribution, the cost misclassification, and size of training and test dataset. Okay. So based on the sample that we get, we know that if we have higher sample size, we will be able to increase the accuracy. Okay? And but how much? Because the maximum accuracy we get will be here. But how much sample size that you need? Just enough for you to get the best accuracy, because we do not want to have a bigger sample size because it will increase the training time. Okay, so we want to have somewhere here. So this is what we call the learning curve that show how accuracy changes with varying sample size. Okay? So this one requires a sampling schedule for creating learning curve. So the effect of a small sample size bias in the estimate. So if you have small sample size, so the blue one is the bias lah. So you could have the error this big. Okay? So that's why it's better to increase the sample size in order to increase the accuracy so that your bias will be smaller. Okay. So when we discuss about the K-fold just now, so initially they have this, they say 2/3 for training and 1/3 as the testing. So this is what we call the hole out. We can also have the random subsampling. So so this is similar to the K-fold. Okay, K-fold, where you take one, no, for yeah, where you take one as the validation and the other two. So this is what we say threefold. Okay, threefold validation. Okay, for we also have the tenfold cross validation. This is just example. So we take one of them as the testing and the other will be the training. We also have the leave one out. So leave one out is for the test and k minus one remaining. No, this is the other way around. We use this one for training and the other will be the testing. So this is leave one out. Okay. So all this we can put in our design, our experimental design. So why you choose this, why you not choose that, and so on. Okay, or even you can compare by having cross validation and not cross validation. Which one will give you the best accuracy? Okay. We also have this what we call the stratified sampling, in which we divide them into the classes first. Then we perform the sampling so that we have equal number of uh, all the type. So we do not want to have imbalanced data set. Okay, so this one I explained that one already. Okay, now we look into the ROC method for model comparison. Um, how we draw the ROC curve for a single classifier? Okay, so this one was developed in 1950s. Basically, they characterize the trade-off between the positive hits and the false alarm. So we are looking at the positive hits and also false alarm. So we plot the true positive rate against the false positive rate. Okay, so the performance of each classifier represented as a point on the ROC curve. So we want to look which classifier is best depending on area under the curve. Okay, so if you look at this diagram, one-dimensional data set containing two classes. So we have positive and negative, and any point located at x greater than t, so greater than t here, is classified as positive. Okay, so if we have the blue one as your actual one, okay, so everything on your right here will be positive. So meaning that we have all of this here is false positive because they are negative. Okay, so this is negative. So meaning that this is your true positive, this is your true positive. But beyond here, we are saying that we have negative. So that's why they call it false negative. Okay, because they're still okay. This is the positive class. This is the negative class. Um, the blue one is negative. The red one is positive. So that's how we interpret this one. So when we look at this diagram here, um, when the TP is 0.5 and also the false negative is 5, true positive is here, and then your false positive is here. So basically we are here. Okay. So at threshold T, because your true positive is looking at here, your true positive. Wait, yes. Okay. So true, no, we are looking at this. True positive is here. Then based on the curve that we have here, your false positive is 0.12. Okay. So based on this curve, we can compute this one because the true negative will be 1 minus this. And then this one also can be computed based on 1 minus true positive lah. Okay. Okay. So similar example here. So we are saying that M1 is better for small for false positive rate. M2 is better for large false positive rate. Okay. So the best thing is we compute area under the curve, area under the ROC curve. So the ideal one is here, which is 1. Random guess will be here, 50%. Okay. So now let's take a look at how do we plot this graph. Okay. Let's suppose we have this data lah. This data, but for us to um, plot the ROC, we have to look at the probability of having positive class given all the attribute. Okay, so you know this one can be computed using the naive bias given all the attribute. What is the probability of having positive class? Okay, so we have rearranged the order here. So the highest one will be on top and the lowest one will be here. Okay. So if we rearrange them in this order, okay, this is your initial setting. So we need to compute what is the true positive. So basically here we draw a line here. Ignore this spike. So whatever you have here will be your true positive. Positive lah. So whatever you have here will be your negative. So we notice that this is okay, this is okay. Okay, so that's why your true negative is 5 here. But we have false negative. So this is positive, but classified as negative. So we have false negative 5. False negative will be 5. Okay, so your true positive rate will be 0 because 0, your false positive rate will be 0 as well. Okay, can you follow me? Okay, now we go to the second level. Okay, now we are saying that in this case, okay, everything to your right will be what? Positive kan? Everything to your left will be negative. Okay, so this is considered as true positive. Okay, true positive will be 1, and then at this side we will have 5 true negative and 4 false negative. Okay, then we can compute the true positive rate here. Okay, so the true positive rate will be 1 over 5. Okay, so next one will be here. So this is positive, this is negative. Okay, so we have two true positive, and then over here we will have 5 true negative and 3 false negative. Then we can compute the true positive rate. So we will compute this one, continue. So for example, like this, if we are here, so we have true positive 3, and then we have false positive 2. Okay, and over here we have 3 true negative and 2 false negative. Then we can compute this. Okay, so we will complete this until here. Okay, so based on these two value, we can plot them. So this is the plotting that we have. So now we can compute area under the curve. Okay. Okay. The last one is just to give you example because I have reorder this one, the symbol here. So this is only for this. So for your practice only, so you can perform this with different class label here, and then you draw, and then you compare which one is better. Okay, so the area under the curve is just simply find area under the curve. So you compare which one is better. Okay, any question? If you okay, can you type number 1? Okay, so by now you should be able to evaluate the performance of the algorithm, or maybe if you are given the ROC. So normally they say area under curve, AUC. When you read a paper and it said AUC for the ROC, it refers to area under the curve. So the higher they are, the better is the algorithm. So maximum value for area under the curve will be, what is the maximum value? Can you type the maximum value that you can get for the curve, for the area under the curve? 1, kan? Yes, 1. Okay. Um, that's all for this session. I hope you um, learn how to evaluate the performance of the algorithm, and you understand how to construct the ROC.